Alright, so we've got a few problems. We're wrapping up chapter 5. So basically we're just going to categorize our energy situations into two types. So one where work is being done on the system, so the total mechanical energy will change, and one where there is no work by an external agent done on the system, and so total mechanical energy is conserved. So basically all these problems, we're going to handle them using one of these two expressions, right? Work is done, energy changes. Work isn't done, energy of the system remains constant. All right. So here we've got a block that's compressing a spring, and it's a distance x initial from here, which we're calling x equals 0. So we get the spring constant of the spring, and we've got how much the spring is compressed. So that's point A. So we let go of the block. The spring is going to apply a force on the block. It's going to slide. Let's just pretend this is curved here, right? So the block is going to slide smoothly up this surface. The surface is frictionless, right? So there's my hint that there's no non-conservative force in question, right? So it's a frictionless surface. That's going to tell me total mechanical energy is conserved. I've got the angle of the incline, and there are two questions. So there's a question about the block at point B when it's halfway up the incline, right? You see this? This is h. At point B, this is 1/2 h. Then there's a question about the block when it's all the way up the incline. So the first question is find the maximum distance d, this straight line distance. The block travels up the incline. And then the second part is how fast is it going when it's halfway up to its max height. So when they're talking about max height, that's point C. Like the block is going to reach a point here, and then it's going to come to a stop, right? Because it's hit an incline, it's under the influence of gravity, it's going to accelerate down the incline, it's going to slow down, eventually come to a stop, right? So we know that from like our kinematics and our Newton's laws examples. So the first question is, we got to talk about point C, right? And we're looking for the straight line distance d. Okay, how far up the incline does it go? So what I like to do is I like to split the situation up into points A, B, and C. I just identify all the types of energy that the system has at those points. So at point A, the spring is compressed. So there's a type of energy that the system has, and that's the spring potential. Alright, so I'm going to write my expression for the spring potential. I'm going to say the gravitational potential at this point is 0, and the kinetic energy is 0. Okay, spring is compressed, mass is at rest. So vertically, in the y direction, I'm still in amber. So I'm saying down here at the lowest point that the mass is in this situation, it has a gravitational potential of 0. So that means as it slides up the incline, it's going to have a positive gravitational potential the farther it goes up the incline. So down here at 0, anywhere up here it's going to be some positive value. So we start off point A, it only has a spring potential. Once it gets to point C, it's up the incline a little bit, so it's got a gravitational potential with that's dependent upon its vertical position. Okay, so it's a distance h over 2 above the ground. All right, so it's got a gravitational potential of mg 1/2 h. All right. There's no spring potential in the system anymore because the spring is no longer compressed. All right, the spring is in equilibrium, the block is not in contact with it, so there's no spring potential. But in this second part, it's asking how fast is the block going when it's halfway up to its max height. So we know that it's got a speed v, it's going up the incline, gets to here, it's still moving. So it's got to have a kinetic energy. So I'm going to call that v1. It's got a velocity v2, or v1 right there at point B. So it's got a kinetic energy and it's got a potential energy associated with its vertical position. Point C, it's at max height, so we know it doesn't have a velocity, still doesn't have a spring potential because the spring is at equilibrium again. Kinetic energy is 0. It now has a gravitational potential mgh because it's at its max height. So I'm concerned with these three events, right? A, B, and C. I don't care about what's happening here or in between, right? I'm just looking at how the energy is transformed from points A, B, C, etc. Okay, so I don't really concern myself with what's happening in between. So let's set up an energy equation to answer the first part, right? Find the maximum distance d the block travels up the frictionless incline. Now, if you notice, d is not the same as h, right? So I can't solve for h. I got to find a relationship between h and d. Fortunately, I've got this angle of incline theta. It's a right triangle, so I'll just do a little bit of trig and figure out that relationship. So here's h, max height. D is the length of the incline. H is the opposite side. D is the hypotenuse. So sine theta is h over d. So I've got this relationship. H is d sine theta, or d is h sine theta. So you could solve for h, right? You could solve for h, plug it in here, and then calculate d. Or you could plug d sine theta in for h in your expression. So it's really however you want to handle it in this case. I'm going to solve for h first, and then I'm going to plug it in here and solve for d. So we know there's no work being done by a non-conservative force, so the total mechanical energy of the system at point A equals the total mechanical energy at point C. So the total energy at A is just the spring potential here. The total energy at point C is just the gravitational potential energy here. So I'm setting this term equal to this term, and I'm going to use that to solve for H, right? Initial spring potential equals final gravitational potential. Algebra is not too bad, just divide both sides by mg. You get h by itself. We've got the spring constant. We've got the amount that the spring is stretched. We've got the mass of the block, acceleration due to gravity. We can plug everything in there. And we've got a height, a vertical height h of 0.63 meters. But I'm asked for d. I'm asked for the distance up the incline, so I'm going to plug 0.63 meters here, plug 30 degrees in for theta, and we see that the distance it travels up the incline is 1.28 meters. Again, I know that energy is conserved. There's no work being done by an external agent, so I can just set the energy at point A equal to the energy at point C. Don't care about what's happening in between. I know all the energy the system has initially has to equal the energy that the system has finally. Okay. Now, the second part, we want how fast the block is going when it's halfway up to its max height. Right? So now it's up vertical height h over 2, and it's I believe it should come out to be where it's actually halfway up the incline. But it's a vertical distance h2. It's also moving. So just like I did with the first part, I'm setting the initial energy at point A, that's a typo, sorry, I'm full of them today, alright, to the initial energy at point B. Okay, so that should be a B there, sorry about that. So I set the initial spring potential equal to the total energy at point B, alright, point B. So it has gravitational and kinetic at point B. So set the spring potential from point A equal to the gravitational potential and the kinetic energy at point B. So I substitute my expressions in. Notice everything's got a 1/2 in it this time, so that's pretty nice. Right? I don't have to deal with these fractions. I can cancel out that 1/2. I'm looking for v1. Right? I'm looking for the speed. When it's at point B. So I'm going to solve this for v1. Subtract this term from both sides. mgh. I get k delta x squared minus mgh is mv1 squared. Alright. Not every term has a mass, right? Masses have canceled before, but when you're dealing with a spring, you could have a spring potential term that doesn't cancel out, or that doesn't have a mass in it, so it doesn't cancel out. So just watch out for that. I'm going to divide both sides by m, so I get this expression here for v1 squared take V1, or take the square root of both sides. I get my expression for V1. I have all these values: spring constant, displacement, mass, the height. Right, the height I found over here, which is good. Okay, so I need that for the second part. Still got the mass. Throw everything in there, calculate it, and I should get a V1 of 2.5 meters per second. Again, is it positive? Is it negative? Doesn't matter, because I'm just asking how fast it's going, right? Energy problems, I'm concerned with the scalar quantity, right? Usually I'm just concerned with the speed. All right. So again, all the stuff that happens in between these points, I'm not concerned with. You set initial energy at some point equal to final energy at some point. Identify the types of energy that the system has at each of these points. Set them equal to each other. Do the algebra, and you can arrive at your solution. All right, so stunt person problem. We got a little bit of trig that we have to rely on here, because this is a unique situation. It's a conservation of energy problem. All right. So somebody is swinging from a cable, or well, in this case it's a vine, so it's like a stunt person on a movie set or something. So the vine is 30 meters long. So we're picturing a person kind of standing on a platform, holding on to this vine, and the vine is at an angle of 37 degrees with the vertical. What does that mean? I'll show you the picture I drew, and then I'll show you how to identify what that angle is. So it swings down, and it comes to the bottom of the swing, but that person is moving, and we're asking for that person's speed when they get to the very, very bottom of their path. So we can picture it like this. The person starts at, I'll zoom in a little bit here, there we go. The person starts on some platform, right? It's a height h. Where is that? They don't give it to me. Great. Okay. So I'm just going to say that the height, right, is h for now. So the person is starting with some gravitational potential. Steps off the platform, swings down, follows a circular path, right? Follows a circular path like this. Okay. And then it gets to the bottom of the swing, and then it's got some speed. So that's what we're looking for. Initially, what type of energy does the stunt person have? It's got gravitational potential, mgh. What's h? I don't know, but I should hopefully be able to figure that out, because I'm going to have to know what this is. Right? I'm going to have to know what this initial gravitational potential energy is. So the stunt person has a kinetic energy at the bottom. Again, I'm in amber, so the lowest point of this stunt person is u equals 0. Right? That's my gravitational potential energy, 0. All right. So I set the initial gravitational potential equal to the final kinetic, and the masses cancel, right? I could solve for the final velocity. It'll look real nice. It'll look something like root 2gh, you know, something that'll come out of my kinematics. Here's my problem. I'm not given h. I'm not given h. Now what I see a lot of people do in this problem is just say, well, I got a distance, right? I got an L, so I'll just say L is h. That's not true. Right? This distance h is not the length of the cable. Okay? And actually in this problem, h is less than the length of the cable. So we have to find out what this is with respect to the length of the cable. Now this 37 degrees, it says makes 37 degrees with the vertical. So the stunt person gets up on the platform, and the vine is making an angle of 37 degrees with this. Okay, so 37 degrees with the vertical. Alright, so there's my theta. So here's what happens. What's the relationship between h and L? If the stunt person's up here, this length right here, we're assuming that the stunt person is keeping the vine taut. Right? So this is L. This is L right here. This is L right here. So I've got to figure out what h is with respect to this length that I know. So I drew the picture again. Okay, here's h. This is the height that the stunt person is. This total distance is L. This total distance is also L. So I drew a right triangle using this length when the stunned person is on the platform. This L is the hypotenuse. This is the adjacent side. I'm calling it A. From the top of the vine to point H, where the stunned person is, I'm calling that A. Alright. So here's my right triangle, there's my angle, there's my adjacent side, my hypotenuse. So these two lengths, A plus H, are equal to L. So this length, this side of the triangle, plus the height of the stunned person equals the total length of the vine. So A plus H equals L. I can subtract A from both sides and get H equals L minus A. So great, I just introduced a new variable. What's the point of that, right? Why would I introduce a new variable to get rid of, to try and get rid of another one? So here's the relationship between A and L. A is the adjacent side, L is the hypotenuse. Cosine theta is adjacent over hypotenuse, A over L. So I introduce A as a new variable, but I use trig to define A in terms of quantities that I know. So if I multiply both sides by L, A equals L cosine theta. So now I have a new variable, I introduced it, but I can now write A in terms of L and theta, which I know. So H, the height of the stunned person, is actually L minus L cosine theta. Alright, so this right here is A. So I can take L minus L cosine theta, substitute it in for H. Now I substituted it in for H before I solved for V final, which is okay. You can wait until the end, it's no big deal. M's go away. Now I've got everything that I need to solve for V final, right? M's go away, multiply both sides by 2, V final squared is 2G, the quantity L minus L cosine theta. I can take the square root of both sides. I've seen some people factor this out before, write it like 2GL times the quantity 1 minus cosine theta. That's fine. Take the square root of both sides. I know G, I know L, I know theta. Theta was 37 degrees, sorry I didn't plug it in there. So the final velocity is 10.9 meters per second. Again, I'm just asked for the speed, don't have to worry about the direction. Based on my picture, it's the positive x direction, but again, I don't care. Alright, so stunt person, anybody swinging from a rope, anything like that, make sure you handle it like this, okay? H is not equal to L. You got to find the person's gravitational potential, but you have to write how high they up are on the platform in terms of the length of their cable or their vine, whatever, okay? So make sure you handle it that way. Alright, what's next? So these next two problems might look a little familiar to you. They're images of problems from chapter 4, right? Newton's second law. So we're going to release this system from rest, okay? I made the hanging block larger than the block that's at rest, so we can kind of intuitively predict that M2 is going to pull M1 to the right. So again, we got this two-dimensional problem, but the two objects are going to have the same acceleration, the tension's going to be the same everywhere, right? So again, I'm going to pick my convention that the positive direction is M1 moving to the right and M2 descending. But I'm dealing with energy, all right? I'm dealing with energy, so I have to, I don't necessarily have to worry about the directions of these objects, okay? So it'll say it says how fast is the system moving when the hanging block has fallen 0.75 meters. The hanging block is 8 kilograms and the other is 3 kilograms. So I'm going to use energy principles here to solve for the speed of the system. All right. So just like we did in chapter 4, their accelerations are going to be the same because they're connected. Their speed at any time is also going to be the same. Okay. So I'm looking for V final of the system. All right. So one thing I noticed, I just noticed this while making the video, is that I solved this problem as if there was no friction. All right, so I'm doing a conservation of energy problem. So those of you who are watching the video, right, you'll see that there is a coefficient of friction in the problem between the block and the surface. So what I'm going to do is I'm going to ignore this friction for now. All right. So I'm going to solve it as if the surface is frictionless. Okay. And then I'll go back and I will rework the problem and I'll attach a new solution to where we have to account for friction. All right. So this first example, I'm going to neglect the friction, and then I'll go back and I'll solve the problem with friction. Okay. So let's write all the initial energy of the system. System is released from rest, so there's no kinetic energy. Block 1 has no kinetic energy. Block 2 has no kinetic energy. Block 1 has some potential, right? I'm in amber. I'm going to say the lowest point that M2 can fall is 0 potential. All right. So M1 has some potential, right? It's up above here. It's got some potential. I don't know how high it is. So that's going to be an issue. So I don't know what that is, right? But the potential of M2 is mgh. And what is the height of M2? It's 75 meters above where it's going to descend. Okay, so it's up here at 0.75 meters. It's going to descend down to 0 meters. All right, so I've got an initial gravitational potential for M2 and nothing else, except for this guy. Except for this guy. I don't know what's going on with this guy. So let's release it. M2 descends, right? Now M2 has no gravitational potential, right? It's fallen 0.75 meters. I picked that point to be 0. M2's got no gravitational potential. Both blocks have a final kinetic. They both have a final kinetic because they're both in motion. So they both have a 1/2 mv final squared. Their masses are different, but they have the same final velocity, right? So I don't have to give these subscripts. These are the same variables. Both the objects are going to have the same speed. What happened to M1's potential? It's still up here, right? It's still up on the ledge, still up on the surface, okay? But even though I don't know what the potential is there, it didn't change. So earlier I said I'm not always concerned with the individual gravitational potential of an object at different locations. I'm concerned with how it changes. So I don't care whether M1 has a gravitational potential or not. I know that that value doesn't change because it's only moving in the x direction, right? It's not moving up or down, so its gravitational potential doesn't change. So I can ignore these terms completely. All right, so I don't even have to account for the change of potential of M1 because it's 0. Again, I'm working this problem to where there's no friction. I'll fix it. I'll include friction in a later example. All right. So the initial energy, what is it? It's just the gravitational potential of the block. Final energy is the kinetic energy of both M1 and M2. So set initial gravitational equal to the final kinetics, and I'm looking for V final. So here's what happens. If you got a multiple block system, right, they'll both have their own individual kinetic energies. They both have a 1/2. They both have a V final squared. The fact that they have the same speed is important here. All right, they both have the same V final. So I'm factoring out a 1/2. I'm factoring out the V final squared, and what I'm left with is the sum of the two masses. And this is a nice expression too, right? Because this is just saying the kinetic energy of the system, right? 1/2 the mass of the system, final velocity squared. All right, so we can do this as long as the objects have the same final speed. So here's V final. That's what I'm looking for. Let's multiply both sides by 2, divide both sides by the sum of the masses, M1 plus M2. So V final squared is 2M2. Keep your subscripts straight here. All right, make sure you practice good bookkeeping here because these subscripts can get tricky. 2M2GH over M1 plus M2. Take the square root of both sides. I've got the masses of both blocks. They were given to me. I've got the height of M2 initially, 0.75 meters. I can plug my values in and I get a speed for both blocks of 3.3 meters per second. Okay. Conservation of energy. Initial energy equals the final energy. You'll have all the terms you'll need, or you'll at least have a way to find all the values that you need to get that final velocity. And again, I'll go back. Sorry about that. I neglected the friction the first part, so I'll come back and I'll rework that system, or rework this problem with friction. Alright, so here is a problem where I did not neglect the friction. I saw the picture and the surface was rough, so that reminded me of friction this time. Okay. Now I've got three objects. This should look pretty similar to a WebAssign. Matter of fact, I probably, at risk of incriminating myself, I probably stole the image from the same textbook. So we're doing a very similar problem to one that's on the WebAssign. The WebAssign might not have friction, right? So we'll talk about how we account for that. So I've got three blocks, three masses, very similar system to this. Okay. M1, M2, M3, I know them, right? I know their masses. I've got a coefficient of friction of 0.3 in between block 2 and the surface. So it says find the speed of M3 after it moves down 3 meters. So M3 is going to descend 3 meters. I'm looking for the speed of M3, but as in the previous example, I know all three of them are going to have the same speed because they are connected by a string. So I'm going to set this up. I'm going to look at the initial energy of the system, the final energy of the system, and this time I'm going to account for the work done by friction. Alright, so here are my diagrams here. This is before the system moves. Alright, M1 and M3 are at some given position. We're just going to say it's not exactly perfect, right? They're not lined up perfectly. But I'm just going to pick a point right here and right here. I'm going to say that's h equals 3 meters. So I'm going to say M1 and M3 are both at a vertical height of 3 meters. I'm an amber again. So down here is going to be 0 gravitational potential. Whenever M3 descends 3 meters, it's going to have no gravitational potential. Alright. So right here, any block that's right here is going to have a gravitational potential of mgh. Again, just like the last problem, M2 is going to have a potential. I don't know what it is, but it's not going to move in the y direction, so its potential is not going to change, so I can ignore that. Once you let go of it, M3 will descend, M2 will move to the right, M1 will ascend. They're all still connected by a tension, right, or by a string with tension in it. So they are all going to move the same distance, right? M3 is going to descend h, M2 is going to move to the right h, M1 is going to ascend h. All right, and now they're all going to be in motion, so they're all going to have kinetic energies associated with them. So initial energy, no kinetic energy, the whole system is at rest. Who's got an initial gravitational potential? M1 does. M1's got an initial gravitational potential of M1gh. M3 is going to have an initial gravitational potential of M3gh. Again, mass 2, don't care, its gravitational potential doesn't change. So this is the initial energy of the system. Final energy, all three blocks will have kinetic energy. Okay, so these are my kinetic energy terms for all three blocks. Like the previous problem, I can factor out the 1/2, factor out the v final squared, and I can rewrite that as one kinetic energy term. How does the potential energy change? I know M3 descends, so M3 is going to have a final potential energy of 0. Okay, but M1 doesn't fall, M1 ascends, so the potential energy of M1 actually increases. So it goes from mgh to mg2h. Right? It was initially at a height h, it ascends another height h, so its total gravitational potential is mg2h. Alright, so I wrote it as 2 m1gh. So m1's gravitational potential actually increases. Now, total mechanical energy is not conserved because there's a non-conservative force due to friction. So I need to find what the work being done due to friction is. And friction is acting on M2 only. So I just have to find the work done on M2. M2 moves a distance h. Down here I call it d, but I'm going to replace that with h. It moves a distance h to the right. Friction is opposing that force, so it's applying a force in the negative x direction. M2 is moving in the positive x direction. So here's a free body diagram for M2. It's got the frictional force in the negative x. I drew the displacement vector to show you that it's moving in the opposite direction. So use my definition of force. I've got the frictional force times the displacement. I'll replace that with h times the cosine of the angle between the vectors. The angle between these vectors is 180. Cosine of 180 is -1. What's the frictional force? Frictional force is mu times the normal. What's the normal force? In this case, the normal force is equal to the gravitational force, m2gh. Alright, so you can fill in those vectors on this free body diagram to verify that. The normal force is equal to the gravitational force, so I've got mu m2g, replace d with h, because that's how far it moves, times the cosine of 180. Cosine of 180 is -1. Negative mu m2gh. That's the work being done. Okay. Let's go all the way back, because I said earlier that we're going to deal with these two types of scenarios. Up to this point, we've been dealing with energy conservation. Now, energy is not conserved because there's work being done due to friction. So work is equal to the change in kinetic energy plus the change in potential energy. We don't have any springs in this problem, so we don't have to worry about the spring potential, just gravitational potential. Okay. So we're back here. Work is change in kinetic plus change in potential. It's only gravitational. So I'm going to use this, and I'm going to split it up. Split my deltas up into my final minus initials. Final minus initial. Okay. I have a work term here, right? You got a work term. So I know there's a final kinetic. The system has a final potential. The system has an initial potential, but it has no initial kinetic because it's released from rest. So now I'm substituting my terms, right? I'm looking at this. Ooh, it's getting pretty rough, right? There's going to be a lot of terms here. Your algebra is going to take some time. But we know everything that we need to solve for V final. There's my expression for the work. I just found that. Okay, so if there's ever friction, make sure you can calculate the work due to friction this way. The final kinetic is the sum of the kinetic energies of all three blocks, 1/2 m1, m2, m3, V final squared. That's the final kinetic of the system. Final minus initial. Make sure you keep these straight too, okay? Don't put your initial term first. Go back up. What's your final potential? Who's got potential at the end? Just m1, right? m3 doesn't have one, m2's doesn't change. m1 has a final potential of 2m1gh. So there it is. Okay. In this situation, more than one object has an initial potential. So I'm subtracting the initial potential term from the final potential term, but there are two initial potential energies, so I'm putting them in parentheses. Okay, so I'm subtracting both of these initial potential terms. Alright, so I put it in parentheses. I'm going to distribute that. Right, so I'm going to get negative m1gh minus m3gh. So once I do that, I'm getting all the terms that don't have V final in it on the left side. So I'm subtracting this term from both sides, and I'm adding those two terms to both sides. All right. So I get the work minus 2m1gh plus m1gh plus m3gh. All of that's on the left side for me, and then I've got my final kinetic term on this side. All right. And so I'm switching it around. You know, I like the variable that I'm looking for to be on the left side in case you haven't noticed. So I'm just flipping the equation around. All of these terms have a GH in it. If you notice all of these, GH, 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 GH. So I'm going to factor that out. That's just to make my calculations easier. All right. So I factored out a GH, and I've got all this stuff in parentheses, right? But I know mu, I know all the masses, I know G and H. Okay. 2m1, or negative 2m1 plus m1 reduces to negative m1, right? So I'm just combining these two terms right here into negative m1, just cleaning it up a little bit. So now here, I need B final. So I'm multiplying both sides by 2, again, multiply both sides by 2, divide both sides by the sum of the masses. Alright, so this is my expression for V final squared. Excuse me, I'm ready to take the square root of both sides. I know all the values of everything in here. I'm ready to plug it in, do my calculation, and I get a final speed of 3.1 meters per second. A lot of objects, right? Be able to handle multiple objects, identify the type of energy that the objects have before and after, and make sure you can account for how the potential changes. All right. Most of the time we've been dealing with something starting with an initial gravitational potential and then it falling and then going to 0, right? Or it's got an initial potential of 0 and it's thrown up in the air. So just make sure that you can keep track of how the potential changes for each object, right? You see M3's potential decreased, but in doing so we increased the potential of M1. Okay. Alright, so I'll do one final video. I'll rework this problem right here with friction. So this will look very similar to this 3-block system when I do it, because now I have to account for work. So I'll rework this problem, accounting for the work due to friction, and then I'll discuss a little bit about power. It's kind of a small portion of this lecture, but we'll talk about power. It's a pretty straightforward concept, so I'll just talk you through a couple examples, and we'll be done chapter 5. All right, see ya.